A very good morning to scientific, innovative, and curious minds of the country. I am delighted to welcome esteemed guests, professors, and scholars to the fifth Professor ML Kapur Endowment Lecture. I am Anup Gupta, a PhD research scholar, and I have the privilege of hosting this remarkable event. We are honored to have with us today Dr. R. Balamurali Krishnan, an outstanding scientist and director at DMRL DRDO Hyderabad, who will delve us into the intriguing topic of the value of death in the context of advanced materials. This lecture is a collaborative effort organized by the Department of Metallurgical and Materials Engineering, IIT Roorkee, in conjunction with the Indian Institute of Metals, Roorkee chapter. Without further ado, let's embark on this enlightening journey together. Welcome once again and thank you for joining us. Today, we are gathered here to celebrate knowledge, wisdom, and the spirit of learning. Let us commence by inviting our esteemed dignitaries to grace the stage. I kindly request Professor B.S.S. Daniel to accompany our esteemed guests onto the stage. Kindly give a big round of applause. Thank you, guests, for honoring us with your presence. Your wisdom and leadership inspire us all to strive for excellence in our endeavors. Now, I kindly request everyone to stand for the Kulgit, the Institute's anthem.
जयति जयति विद्या संस्थान जयति जयति विद्या संस्थान हिंदी शृंगो से अभिनंदित गंगा जल करते कलना जयति जयति विद्या संस्थान जयति जयति विद्या संस्थान शिक्षा आदर्शों में उन्नत जीवन शिल्पी भूरचनारत शिक्षा आदर्शों में उन्नत जीवन शिल्पी भूरचनारत श्रमं विना न किमपि साध्यं यंत्र कला कौशल्यभियान जयति जयति विद्या संस्थान जयति जयति विद्या संस्थान जन जीवन प्रासाद उठाकर सेतु बांध भूखंड जुड़ाकर जन जीवन प्रासाद उठाकर सेतु बांध भूखंड जुड़ाकर अंतरिक्ष में यान उड़ाकर नवयुग को देता आह्वान जयति जयति विद्या संस्थान जयति जयति विद्या संस्थान सर्जनित जीवन नित अर्पित धरा स्वर्ग शोभा कर निर्मित सर्जनित जीवन नित अर्पित धरा स्वर्ग शोभा कर निर्मित वैज्ञानिक युग पथ में मूर्ति भू पर लाता स्वर्ण विहार जयति जयति विद्या संस्थान जयति जयति विद्या संस्थान नई प्रेरणा से दीपित मन नव स्वप्नों से हर्षित लोचन नई प्रेरणा से दीपित मन नव स्वप्नों से हर्षित लोचन नए सत्य की उर्मी धड़कन, ध्येय राष्ट्र जीवन कल्याण। जयति जयति विद्या संस्थान, जयति जयति विद्या संस्थान। हिंदी शृंगों से अभिनंदित, गंगा जल करते कल्याण। जयति जयति विद्या संस्थान, जयति जयति विद्या संस्थान। जयति जयति विद्या संस्थान, जयति जयति विद्या संस्थान।
Now I invite our honored guest on stage to mark this auspicious event with a lamp lighting ceremony. I would request Dr. R. Balamurali Krishnan and the guests to inaugurate this session by lighting the lamp.
शुभं कुरुत्वं कल्याणम्, आरोग्यं धनसम्पदः। शुभं कुरुत्वं कल्याणम्, आरोग्यं धनसम्पदः। शत्रुबुद्धिविनाशाय दीपज्योते नमोऽस्तुते, दीपज्योते नमोऽस्तुते। दीपज्योते परब्रह्म, दीपज्योते जनार्दन, दीपज्योते परब्रह्म, दीपज्योते जनार्दन। दण्डादीप नमोऽस्तुते, बोधिसत्वरूपस्थं, ज्योतिषां प्रपुराव्ययः, ज्योतिषां प्रपुराव्ययः। युक्ते पुत्रांश पतिर्स्वच्छामि मे सदा। तपेरस्तव तपेरस्तं समाप्य, यावत् सूर्योदयो भवेत् यस्य।
Now, as we continue with the program, it's time to formally welcome our guest by presenting a bouquet of flowers. With great pleasure, I request Head of Metallurgical and Metals Engineering, IIT Roorkee, Professor B.S.S. Daniel, to kindly present flower bouquet to our esteemed guest and speaker of the day, Dr. R. Balamurali Krishnan. Dr. R. Balamurali Krishnan is an outstanding scientist and director, DMRL, Defense Metallurgical Research Laboratory at DRDO. Let this gesture symbolize our deep appreciation for their presence and contributions to this occasion. Now I would request Professor Saurabh Das, Secretary IIM Roorkee Chapter, to kindly present bouquet to our guest of honor, Dr. Seema Vinayak, Director DRDO Industry Academia, Center of Excellence, IIT Roorkee. Please give them a big round of applause. I would like to request Professor B.S.S. Daniel to kindly present bouquet to Professor Ashwini Kumar Sharma, Officiating Director, IIT Roorkee, who has kindly consented to preside over this function. Thank you, Professor Daniel. Moving forward, I request Professor B.S.S. Daniel, Head of Department Metallurgical and Metals Engineering, IIT Roorkee, to introduce the department and the ML Kapur Lecture Series. Kindly welcome him with a huge round of applause.
Good morning and welcome to this very special occasion. Uh, I want to especially thank Dr. R. Balamurali Krishnan for accepting our invitation and being present. And I also thank all the dignitaries on the dais, the faculty members, retired colleagues, students, and also we have a YouTube audience watching us live, which includes Professor ML Kapur himself. So we welcome all of you on this occasion, the fifth Professor ML Kapur Endowment Lecture, and we thank you for participating in this event. Professor ML Kapur, as you know, he is a well-known figure in the extractive metallurgy discipline. He graduated from BHU with his master's and bachelor's in 1966 and 63 respectively, and also went on to do his PhD at TU Berlin in 1971. He joined our department, which was at that time the metallurgy department of University of Roorkee in the year 1975 as a full professor in 1978. Along with his teaching roles, Professor ML Kapur was a multi-dimensional character. He held several administrative roles. Just to name a few, he was the head of the department twice, 80-83 and 89-92. He was the Dean of Students' Welfare from 1994 to 97 and Dean Development and Planning from 1999 to 2002. And finally, when he retired in 2004, he was the deputy director for a little over a year. And over 35 years, he has contributed in research in the field of extractive metallurgy, covering thermodynamics, kinetic studies in different extraction processes, development of processes for recoveries from waste and energy auditing. He executed a large number of research and consultancy projects from CSIR, BARC, SAIL, BHEL, and also for the German Republic. He published more than 100 papers in reputed international journals. He wrote two monologues, two books, which are quite popular even today, Chemical and Metallurgical Thermodynamics. They are used as text resource books. He is a recipient of the Metallurgist Day Award, IIM, and the Distinguished Alumni Award of PHU, and the Kamani Gold Medal twice in 1981 and 1989. So we are once again thankful that we are to the Dean Resource and Development for providing the funds and creating this endowment to host this Professor ML Kapur lecture. And today we are happy to have the fifth lecture to be delivered by Dr. R. Balamurali Krishnan, who is also the outstanding scientist and director of DMRL, Hyderabad. We would look forward to that. So with that brief introduction, I would like to hand over so that we can continue.
Thank you, sir, for acquainting us with the legacy of Professor ML Kapur and his remarkable contributions to the field of metallurgy, as well as for providing us with an overview of the Professor ML Kapur lecture series. Now I would request Professor Saurav Das, the Secretary IIM Roorkee chapter, to enlighten about the IIM Roorkee chapter. Kindly welcome him with a huge round of applause.
Good morning. It is an honor for me to be here on behalf of IIM Roorkee chapter. Dr. Balamurali Krishnan has many identities: director DMRL, outstanding scientist, excellent metallurgist. But certainly one of his identities is he is a devoted activist of IIM, Indian Institute of Metals, and that actually is connecting me with him. The Roorkee chapter of IIM unfortunately was defunct or was in a hibernation state for a long time. And thanks to the effort of our faculty members, we are able to survive it in the last year. Currently, this chapter is functioning or at least has started functioning properly. And this is the first event that is being hosted in the banner of IIM Roorkee chapter. At the moment, we have 45 life members in our chapter, several student members. The bank account has been opened. The meetings are being organized on a regular basis. And I hope that in the coming years, this IIM Roorkee chapter will actively participate in hosting several such events in the department level, in the institute level as well. And for the students, there are several attractive opportunities for different awards, different rewards for your MTech thesis, for your PhD thesis, which you can aspire for from these IIM initiatives. You can go to their websites and you can look into what you can get. Thank you.
Thank you, sir, for apprising us of the recent initiatives and ongoing endeavors within the Indian Institute of Metals, Roorkee chapter. Now we welcome our guest of honor, Dr. Seema Vinayak, Director DRDO Industry Academia, Center of Excellence, IIT Roorkee, to make us familiar with DIA-CoE IIT Roorkee. Please welcome her with a huge round of applause.
A very good morning to all present in the auditorium. And my special thanks to the head of the department, Metallurgy and Material Science, Dr. Daniel, to have given me this opportunity to talk to you all and be here in the endowment lecture for Professor ML Kapur. And I'm so happy that this is a lecture being delivered by one of my ex-colleagues, because I've been part of DRDO for almost 37 years, and I work closely with the OS and director DMRL. At that point in time, he had just joined when I got a chance to work with him. And it's a premier institute of DRDO, the Defense Metallurgical Research Lab that he's heading now. It's really wonderful to be sharing the stage with him today when he's delivering this endowment talk. And I thank the Dean of Faculty Affairs for being here to preside over this lecture. And I'm thankful to Professor Das for inviting me, for letting me participate in this and giving me a chance to talk to you about DIA-CoE. Long back, I had read a story about a father asking his daughter to open a bottle. And she was a small girl and she was unable to do it. So the father said, do it with all your might. After trying after a few attempts, she got a little frustrated and she said, can't you see, I can't do it. So he says, but I asked you to use all your might. So she says, I've tried. I've used all my might. He said, no, you did not look at me. I'm standing next to you. I have more strength than you. You could have asked me to help. So that imbibed the spirit of the importance, the significance of collaboration in my mind. And I would like to share here that my own PhD wouldn't have been possible if I had not been guided by my then director to go to DMRL and get all their support to understand how the microstructural properties affect the alloy systems that I was working on. And that was for the MMICs, the integrated circuits, where I needed to have zero TCR materials. And the entire microstructure characterization was done at DMRL by the group of scientists that Dr. Balamurali Krishnan was a part of. And that gave me so much of insight into how moving towards somebody to ask for help, to understand, to utilize their complementary expertise, how important it is. And after serving for 37 years at DRDO, I'm really, really very fortunate to come to IIT Roorkee, join the IIT Roorkee family as the director of DIA-CoE, where it is all about collaboration between DRDO and academia. So DIA-CoE, we have about 15 such centers all over the country. And the whole concept started when government said that the DRDO projects, the R&D projects that can be part of those projects that can go to the academia should be given to them. And therefore, it actually makes the whole the human resource working towards the realization of these projects a much bigger team. And we have right now about 700 crores given to about 200 projects across the 15 DIA-CoEs, and they're working the whole aim is to not to have just a basic fundamental research, but to have that fundamental research also targeted towards a tangible product. So if you say, if you imagine what is it that that defense wants, say after 10 years, then the whole thing can be broken up into smaller parts, and each part can be taken up by academia, by different departments to work towards that goal. So that is what we are calling translational research. I will have a chance to talk about it in the interactive session after this, and I look forward to that interaction. And I was just talking to Professor Daniel that when I went through the page which describes the Department of Materials and the Metallurgy and Material Science in the IITR website, I was really impressed. And I told him that I would like to have a similar thing for DIA-CoE. So the moment anybody goes to that page knows all about it. So I think I got inspired by this, by seeing your page on the site. And I will work towards that so that everybody has the information about DIA-CoE instantly. And before I just finish, I would like to say that when Professor Daniel called me to say that we have Professor ML Kapur Endowment Lecture, I only heard the word ML Kapur and I thought, how does he know my father's name, Because that is, just say Aksharasha, not just Kapur, but ML Kapur was my father. And my maiden name was Kapoor, Seema Kapoor. So I was really happy. I'm thankful to you for making me a part of this endowment lecture. Thank you very much.
Thank you, ma'am, for the insights and highlighting the importance of collaboration in the research. Now I would request Professor Ashwini Kumar Sharma, Officiating Director, IIT Roorkee, to share his thoughts on the occasion. Kindly give a big round of applause.
So, dignitaries on dais and off the dais, faculty and students. I think I'm very happy to be here, although as officiating director. But I would like to say that this endowment lectures have been started a few years back to inspire and motivate our young minds and to inculcate the research activities, to inculcate or to start collaboration. And in particular, the spirit behind was to invite eminent personalities, scientists here, and know their views, listen to them, and know their research work. And this would certainly lead to the interactions and would lead to the our PhD scholars, our young faculty members to start with new things actually. To start with, it's not about only like having a job. We have to have that intent and that commitment and passion for research. And was the main idea for starting these endowment lecture. I would like to congratulate, I think, the department for continuously organizing these lectures and inviting eminent personalities. I welcome Dr. R. Balamurali Krishnan, eminent scientist and the director of DRDO, DRML, Hyderabad. Thank you, sir, for coming, accepting our invitation. And also, I would like to thank Dr. Seema Binayak for introducing DOE, this DIA-CoE Center. This is also a new thing in our institute, and I think certainly it will enhance the academic environment and research culture in our institute. We are doing great, but we have to keep doing it and work around to produce things to make aware the general public about research work and also to have products now. It's basic research has to go side by side, but simultaneously, as we are collaborating with DRDO, the research products, maybe in defense or any other area, has to come up from IIT Roorkee. With these words, I would not stand between a very good lecture, which is titled The Valley of Death in the Context of Advanced Materials. So thank you all. Thank you for coming here. Thank you.
Thank you, sir. Your words are always an inspiration to us. Without further delay, let us delve into the most awaited talk of the day. Now it is my privilege to introduce our speaker of the day, an individual whose expertise and accomplishments have gained widespread admiration in industry and academia, Dr. R. Balamurali Krishnan. Dr. Balamurali Krishnan is an outstanding scientist. H has taken over as Director, Defense Metallurgical Research Laboratory, Hyderabad on 31st January 2023. Dr. Balamurali Krishnan obtained his BTech in Metallurgical Engineering from IIT Madras in 1991 and his MS in 1992 and PhD in 1998 in Material Science and Engineering from Carnegie Mellon University, Pittsburgh, USA, following a 3-year postdoctoral period also at CMU. He joined DMRL as Scientist D in 2001. His research interests include the physical metallurgy of high-performance steels and nickel-based superalloys, with a strong emphasis on advanced microstructural characterization and establishing the processing structure property correlations in these important engineering materials. He is also interested in applying modeling and simulation tools to study materials and processes. He has first-hand experience of 25 plus years in working with specialty steels across the entire spectrum from concept to product. His work has been influential in establishing the entire ecosystem, starting from lab scale scientific studies to industrial scale production and certification for final use for the manufacturer of specialty steels for naval constructions. He has a strong interest in fostering enabling interaction between academia, R&D institutions, and the industry sectors toward transitioning concepts to successful products. He has delivered nearly 100 plus keynote invited talks at various R&D institutions, academia, industries, and government bodies. Dr. Bala Murali Krishnan has received the DRDO Agni Award Team Member for Excellence in Self-Reliance in 2005. Hubert I. Aronson Fellowship from Indian Institute of Science in 2010. DRDO National Science Day Oration Silicon Medal in 2011. Metallurgist of the Year Award by the Ministry of Steels in 2017. And Outstanding Researcher in Steel in an Academic Institute and R&D Labs awarded by Indian Steel Association in 2019. Please join me in welcoming Dr. R. Balamurali Krishnan with a huge round of applause.
So, Professor Sharma, Professor Daniel, Professor Das, Dr. Seema Vinayak, all the very senior faculty from IIT Roorkee. It's been a privilege to see you here today morning, sir. I mean, I've heard all of your names earlier, but today gave me a chance. And first of all, I thank you all. And Professor ML Kapur, I understand, is joining us online. So first, I pay my respects to all of you. And it's a great privilege and pleasure for me to be here at IIT Roorkee. I will also begin completing my address by welcoming everybody else, all the other faculty members, the students, and the other ladies and gentlemen present here. Very good morning to all of you. Namaskar. So Professor Daniel has been behind me for several months asking me to give this lectures, and I'm very thankful to him for waiting patiently for me to give him a slot. Actually, I didn't think it'll be this difficult, but I think the last few months, as Dr. Seema Vinayak will know, has been very intense at DRDO, and we have had several rounds of meetings, and we have had to travel. And with the 15 COEs that she mentioned, I think I should also mention that DMRL working on metallurgy and materials, which is kind of relevant to all the other application clusters, whether it is aeronautics, whether it is missiles, whether it is electronics materials, whether it is armament, ammunition. And so DMRL has the largest footprint of the different labs for the COE projects. So, and as director of DMRL, I have to sit in on all those meetings. So that takes a lot of time. But the reason I'm mentioning it here is because it gives us quite a wide perspective of what the areas that we are working on, the products, systems, and platforms that we want to do. And as Dr. Seema mentioned, what is the changing expectations that we have from academia. And well and truly, now DRDO looks at industry and academia as long-term partners for taking us to the next level and beyond. And as the Honorable Prime Minister says, to make us world leaders, at least in a few domains, in perhaps 10, 15 years from now, if not already there. So with this brief introduction, and also I'd like to pay my respects once again to Professor ML Kapur. And he has been a doyen in the field of extractive metallurgy, one that will that unfortunately has had its importance dip in the past, but now and especially in the near future, I have no doubts that it will be very critical as we look to recycle materials. And I'll talk towards the end of my talk about sustainability, as we have to do that and be able to do more with less. Try and convey whatever I would like to convey to you, and hope that much of the message gets across. Does this work? I can do it on the. You see a blank acknowledgement slide. The blank acknowledgement slide says because nothing is everything and everything is nothing. Okay. So if you can thank 2-3 people, you can put their names. But this is based on all that I've learned so far. I am learning what I learned yesterday as well. Professor Daniel put me through a different value of death yesterday. You can ask him after the talk. He said it will be easy and nice. It was slightly different than that. And but anyway, so this is simply to say that anybody and everybody can teach you, and if you are in a receptive mode, and I try to keep myself in that mode, and you learn from lots and lots of people. And as for individual acknowledgements, I'll talk about it in those slides where I've taken things from specific references and books. I put that on this slide. But this really is because all my alma maters, IIT Madras, Carnegie Mellon, and you heard him read my biodata. Then DRDO, specifically several people in DRDO, interaction with other labs, like Dr. Seema's sample was one of the first samples that I looked at when I joined DRDO, and so on and so forth. And we have learned from everything. I mean, I never dreamt that I would work on electronic materials even the day I entered DMRL, because I was going to work on steels and superalloys, which is my domain. But then I ended up spending a lot of time characterizing semiconductor materials and multi-layer structures, whether it is quantum dots or MMICs that she said, and working with GATEC people. I did a lot of that work. And microscopy, again, I was very fortunate because it's a field which everybody relies on, so we get a lot of people coming to us. Likewise, in a slightly larger scale, materials is something that is ubiquitous, as I put in my abstract. Every field needs materials, and being in the metallurgy and materials department, I think each one of you, especially the younger generation, can have a very significant role to play in the coming decades in terms of moving the field forward, moving the nation forward. So my acknowledgements to all who have taught me, all who have learned from me, and all who have been with me. So the title is an inspiration that comes from this. Can I have a caller mic, or do you have to stand here for them to pick it up? Standing in one place and talking is a bit difficult. I like to move around. That's okay, right? For the YouTube, that's okay, no? Is it okay? Can you hear me? Okay. So the title, like I said, is an inspiration from this 2004 book, which was released by the National Research Council in the US. And it was talking about the value, that is the the subtitle there. It may not be very clearly visible. It says accelerating technology transition, but you can read it in the bottom, bridging the value of death for materials and processes in defense systems. So I'm sure all of you might have heard about this, that the value of death is very commonly used in many domains, including science, technology, economy, society, social policies, social sciences. And it simply means, of course, we'll see that in the next slide. It is simply that you have a certain idea, and for it to find full realization, it has to become a product or something. And whatever prevents a promising idea from achieving the final realization. And there are several challenges which could take different forms. The challenge could be technical, it could be social, economic, environmental, and even geopolitical, as is very, very apparent in the current scenario. And so this entire obstacle is called the value of death. This is taken from Professor Dipankar Banerjee at IIC and Jim Williams' article, which came in MRS Bulletin in 2015. And so it is specifically, of course, if you read it as it is, it does not talk about materials. It is fairly generic, but this is in the context of materials. It's basically you have a proof of concept or you have a nice idea and you want to move it to the application, right? And in between is this gap. And the gap, like I said in the previous slide, there are so many things. At the very center, you will have the system constraints, design and operational uncertainties, the performance debits that you will get as you scale up from concept to lab scale to pilot scale and then to full production scale, right? So that is the core technical challenges. And there could also be market, investment, production cost, cost to qualify. So these are the economic challenges. And outside that, then is the ecology, supply security and scarcity, geopolitics and the supply chain. And sitting in a materials department, sitting as scientists, sitting as engineers, you have a greater control other than perhaps inherent limitations, but you have more control over the core, and the farther you go out, the less control you have. So you almost have to adapt to the situation that is there, right? See, politics you don't control. The wars and the conflicts that are going on in the world outside today, you don't really control. But still, you will have to move your product to application. And for those of you who are wondering how that war, for example, the Russia-Ukraine war or the Israel conflict, how that will affect us, we are just doing materials research. I'll talk about that in the end. Okay. So this is the value of death that we are talking about. And the real challenge that is in front of us is how to cross this value of death. Okay. In some sense, what Dr. Seema talked about in being able to do more of projects and products, projects not just for science, but also for moving it to products, right? Is in some sense doing this. And the other thing, the word that was used very often was collaboration, which I've been talking to Professor Daniel since yesterday and a few of your colleagues, and today morning again, Dr. Seema emphasized that. Is because when you go to systems and platforms and large things, it's very, very rare. In fact, it's almost impossible for one field to control the whole thing. So you will need materials people, you will need electronics people, you will need chemical engineers, you will need, in fact, you'll need economists, lawyers, everybody, the production infrastructure, the industrial enterprise to see it through to product. So it is rarely a single discipline's adventure, and it needs collaboration truly across spectrum, across specializations, across industries, and across sectors like industry, academia, and R&D. So when we talk about advanced materials, I've already talked about this, that they are ubiquitous. I mean, materials define civilizations, right? We know Stone Age, Bronze Age, Iron Age, then we have the Silicon Age, and today is the age of what? Social media, probably, okay? But the only age where materials don't define it, okay? But even that, okay, is actually truly defined by materials, because all your smartphones, there are 62 elements of the periodic table if you're holding a smartphone in your hand, okay? So I don't remember whether they removed that slide or not, but I had a slide which talked about the materials in a cell phone. And more importantly, even though we talk about materials from Stone Age, there are more engineered and advanced materials in use today than at any other time in history. Okay. But yet, the need for novel and more advanced materials that can survive under extreme or hostile environments. I mean, today we are talking of going to space, going to Mars, looking at that, flying aero engines, flying rockets at hypersonic, supersonic speeds. Supersonic is already there. We are looking at hypersonic now. Okay. So you need materials that would sustain or survive and perform their role in those kinds of environments. And the situation therefore demands, this is what is written there in blue, is a typical material development cycle, which is a design, discovery, development, and deployment. This is the 4 Ds that are central to materials development, and the first 3 are for the development, but taking it to deployment. And actually there is a mini value of death inside each one of those. But the macro value of death is from going from development to deployment. So these are just some, okay. Thank you. Thank you. Nice. So there is an advantage to dropping this on the floor. So more importantly, you want to do this. Pointer is probably not getting that far, but doesn't matter. So the very more important point is to also not only do this, but you also want to do it very, very quickly, because right now the technology generation life cycle is very, very short, and especially like your phones, for example. I mean, they are, and incidentally, gaming and things like your smartphones these days in the world, surprisingly, these are the bigger drivers of disruptive transformations than military. Military used to be the driver of technology for a very long period, until probably even the mid to late 80s or 90s. But somewhere around the 90s, it was the gaming industry that took over, the animation industry that took over. So Walt Disney was driving more technology than the US military, okay, in terms of amount of money that was invested in a particular technology. Of course, it is not the absolute numbers, but if you want to call it as the investment density, okay, or the number of dollars for a particular amount of innovation, that was much higher. It was, I think, 3 times higher for Walt Disney than it was for the US military. So therefore, you have to do it very, very quickly, and you'll have to do it at a fraction of the cost. So this again at the top, this at the left top side is what is in prehistory. You can look at it, this is from the so-called Ashby maps, where you can plot different parameters one against the other. And since I'm talking primarily about, I also come from the domain of structural materials, we are very, very interested in strength to density, because the specific strength, which is the strength divided by the density, because it means it gives you the same performance at lower weight. And as you know, in all these aircraft and rocket, all these structures, weight is even in automobiles, weight is a very, very critical parameter, and you want to keep the weight as low as possible. And therefore, you always plot strength versus density. And on the top, you can look at the kind of materials that were available, and the bottom, it's on the same scale, and you can look how much it is, more densely populated here. And also those 2-3 streaks that you see from the top that are coming there, those actually represent engineered materials, because natural materials tend to be in a very narrow range in terms of properties, each class of materials. But you can take a polymer and have it very high strength and have it very low strength. Okay. So, and likewise, when you make composites, you can do it in that mode. So this is basically that there are you can see there are at least 1,60,000 materials that are available. That means these are materials that have been developed and are in production for some use or the other. This is not just materials that you synthesize in the lab. Okay. And I think this was probably at least 10 years ago. So now we'll enter into this a little bit deeply and enter into the domain of materials. And again, this slide I owe to my seniors because I've used it probably since the date I entered in some form or the other DRDO some 22 years back. We were working on this slide at that point of time, but the basic aspects have not changed. So I tend to use this as my foundation slide for most of my talks. So as far as material discovery, development and deployment are concerned, without looking at other systems, now we are focusing on being able to make one material in one or more mill forms. It could be plates, it could be tubes, it could be bars, whatever it is. Okay, I'm just looking at that manufacturing, and so we call this that manufacturing ecosystem. And if I don't expand the the connotation, the concept to product I'm now talking of for maybe the next 15-20 minutes will be in the context of materials. So now this is very familiar to all of you. How we do this is because we all know our tetrahedron, the processing structure property correlations. Then we add performance to an application and we put characterization and modeling in the middle of the tetrahedron, all that we have been doing, because this is what defines the field of materials engineering, material science and engineering, right? And we are all familiar with the typical R&D activity which goes on in your research, in our labs as well. So you have an intended application, then you translate that application to certain, the material is supposed to deliver a certain expected amount of performance, okay? And then you translate the performance to achievable, to desired properties which the material is supposed to possess if it has to be used for that intended application. And then how you achieve the properties is through microstructural engineering. So basically now you read backwards, you say you do microstructural engineering to achieve desired properties, to deliver the expected performance for the intended application. But the problem statement comes to you usually the other way. Somebody says, I want something to do this. Can you give me that? Right? So that is the application. And then you say, oh, okay, then how long should it last? What should it do? That becomes the performance. And then you look for, if it has to deliver that performance, what are the properties that are? And then you do this. So this looks very simple. This looks very general. And like I said, this has defined our work. I think the material science tetrahedron perhaps first appeared, I'm told, sometime in the mid-50s, okay, in that mode. So you can imagine how much time has passed. But still, that's fundamentally the way we do materials development. And how we do this, we can either play with the composition. I mean, we have the whole periodic table to play with, okay? You can do it through thermomechanical processing, or you do it through heat treatment, which is specifically, especially in the case of many metallic materials. Okay. Now, the moment you want to take it for applications, then you have to worry about scale-up issues for industrial production. So let us look at one example. I mean, a field that I have worked on, where we'll try to make large steel plates for use in naval construction. Okay. So if you want to build big ships, you cannot make samples that are this size. It may have, now this size, I may develop a steel in my lab which has the best properties of any steel that's ever known. Okay. For, let us say, the properties that I'm interested in is strength and impact toughness at lower temperatures, because that's what is needed for typically a hull steel. Okay. Now, if I'm not able to make this very large, several meters in length, several meters in width, and if I'm not able to weld them together to form a ship structure, it will not be useful for that application. So while you in the lab may be very excited, best steel, look at the strength, look at the toughness, great. But tomorrow you're not able to process it. It doesn't leave the lab. It's on this side of the valley of death, right? So one of the things we hope to do with the DIA-CoEs is that you start thinking of problems, potential problems in scalability in the very early stages, because each stage will take a lot of money, right? And you don't want to spend 3 to 5 years developing something and then realize at the end of 5 years, this has great properties, but it is not weldable. Now build a ship with it. How are you going to build a ship with it? Okay. So, like I said, we want, but what we do, that's the subject of a different talk. I have certain slides on that. I will not talk about it here, but during interaction or outside, if people are interested, we can talk about it. What we did was, because in academia, in R&D labs, we were very, very good at the first part of it. But when you really wanted to move to products, which was what the situation we encountered around the time that I joined DMRL, right? We had to start working more and more with industry. And then one of my primary contributions, the area in which I worked, was to try and see, for example, if you study the effect of tempering temperature and time for a particular steel, how can you convert that same information to a safe operating envelope for an industry who's manufacturing it in the scale of tons? Just to especially give the students and the research scholars an idea, see, in the lab, we work at 50 kg melt scale. Of course, in DMRL, we have the capability to melt, to homogenize, to forge, to roll, to heat treat, and to study its properties and study its microstructure. We can do all of this without leaving DMRL. Okay. But if I have to make steel for a ship, the smallest quantity that we normally melt is something like 50 tons. So 50 kgs to 50 tons. Okay. So you have to worry about that. And first of all, what is the R&D mindset and what is the mindset in the industry? Okay. If you look at the left side, and we used to see why this was a problem. I mean, this was a problem I was facing on the ground. Because you go and tell that person, अरे ये temperature थोड़ा change करना है, सर वो lab में काम करेगा, सर इधर कुछ नहीं काम करेगा, हम नहीं करेंगे. Okay. Because remember, he has to be, he is not producing only my steel. He is producing, he is an integrated steel plant. In a day, he melts 8,000 tons of steel. So it's very, very important for us, especially again, this is targeted at students, that you start putting numbers to your thought process. Because otherwise everything seems simple, everything seems easy, and you wonder why others are not taking it forward. Because then you think it's not my job. See, I've shown it at this size. Now you should be able to do it. I've told you how I got this. But it's not that easy. Right? For example, if you take the same tempering case, if I know the temperature at which it should be tempered, and my small furnace in the lab is a fantastic furnace which has plus minus 5 degrees, okay, variability. How do I ensure plus minus 5 degree variability when I have to heat treat a plate which is 8 meters long and do it plate after plate for the next 8 to 10 years? Because otherwise my property will change. The other way, which also we have done, is to make a steel or design a steel which, even if it is instead of plus minus 5, it is plus minus 20, it will still meet the properties. That's a different challenge. But that is science driven by an engineering challenge. Very often, especially in premier institutions, I find, because your exposure starts almost from the pure scientific side, we have a general tendency to look down upon engineering and technology problems. This has crept into our academic system. This has crept into how professors are evaluated for their promotion. This has crept into how you do research. This has crept into how you get your research grants. So we really do not have today proper metrics for assessing somebody's or some groups or some areas' contribution to realization of products and technology. Okay, just keep that in mind. And I'll tell you why this problem has come, right? That's what this slide is about. Because you want to discover new things, right? There's a lot of excitement and fun in that. So at its initial phase in that cycle of deployment, right? And we are doing it at the lab scale. So like I said, we have full control. You can buy virgin raw materials. You can do what you want. You can improve your things. And mind you, even then there are challenges, right? Otherwise, all of you will get your PhD in 2 years. Okay. I'm not saying that is simple. I'm not at all saying that. But that's what you're interested in. But look at industry, what they need to do. First of all, there's a scale up, which is a demonstration they'll have to do. Then they'll have to produce it. and established production. Established production means, see, for example, again, the ship, okay? If you supply, because the ship construction takes 8 to 10 years, okay? And you will be supplying steel for it over 3 to 4 years maybe. So the steel plate that you supply today and the steel plate that you had supplied 4 years ago should have same properties, because they all are welded to be one integrated structure. And that structure is floating miles and miles away from your shore. You have a problem, you call somebody, that fellow comes and repairs your problem. Mid sea, what will you do? Okay. So, repeatability and reliability in the product is of paramount importance. And actually, I do not know about here, but in most undergraduate courses and sometimes even in postgraduate courses, there is no exposure to these kind of concepts. Okay. But for something to be successful, if you have to cross the valley of death, people on this side should talk to people on that side, and people on that side should talk to people on this side. At least. Ideal is if you can talk, if you can be on both sides. But very often that is practically not possible. Which means you should be receptive to listen to their problems and not be dismissive about that. Right? Now what is there here? I have demonstrated here on big plate, you figure out. Go. Actually, we have solved such problems. If there was temperature variability in the furnace, we actually change the reheating schedule to make sure things catch up. You might be surprised. It's like in this room with an AC. I mean, you know, no matter how good your centralized AC is, okay, if you are in the direct line of sight of that blower, that place is colder than the rest of the room. Yes or no? Right? So the room is not at one temperature, right? So like that in the furnace, because there could be a back wall, when you open the front door, there is heat loss. So for the plate to have uniform temperature, you overcompensate the burners in the front, you undercompensate the burners in the back. You have to know how many burners there are. You have to know what is the fuel oxygen ratio if you want to optimize all of this. That's an industry problem. That's a technology problem. So what is there on the left top is what we talked about. Just in case people are confused between repeatability and reliability. Reliability is that product serves its life. Okay. That means a particular product, a particular piece. Repeatability means making like that pieces over so many times. Okay. And I already talked about scalability. So 50 kilograms to 50 tons already I've spoken about. So there, when you say scalability, the process should be scalable and the property and performance should also be scalable. If you recall in that slide that I had shown from Dr. Banerjee and Williams, there was a property debit when you go from concept to production or lab scale to production, because you have a lot more control in the lab. So you'll get the best properties in the lab. But as you take it through to the pilot scale and then to the industrial scale, you will lose some properties. Okay. And then depending upon the particular process, you can look at whether it is batch process or continuous process. Do you have to scale through multiple units or a single large unit? Sometimes the process may be compatible to both. And if it's a single large unit, what you optimize in the lab, you have to go and re-optimize at industry scale. Okay. And this leads to this concept, like I told you, for the tempering temperature and time, the concept of parameter envelopes or process parameter windows. When you have all of this, is only then you have a manufacturing technology. And the DRDO Industry Academia comes in the COE for the industry partner, because the moment you have a promising idea, the idea is to bring them in and to have all three talk to each other so that you understand their problems and they understand yours. So now we talked about having to do that. That is a cycle. Now you want to do that quickly, right? And at reduced cost. So now we'll spend a little bit of time on how we do this. Right. So the typical challenges that you see in the overall value of death situation, some of the factors are that the discovery and development and deployment cycles have very long lead times, and when you, especially when you want to have certification, and it can be addressed, of course, through this integrated computational materials engineering, ICME, the Material Genome Initiative, and artificial intelligence and machine learning, and we'll spend a few slides on those. Okay. Scale up manufacturing technology and stabilization, I've already highlighted to some extent. Ensuring product quality, repeatability, and reliability, also I've highlighted. It is related to that. So somehow, even in the industry, if you get it today, but you are not able to get it tomorrow or day after, it's still not a good technology. It's not a technology that's fit for full-scale production and in use. Now, for demand side issues, and especially for many of the defense products, we have this problem, is that compared to other products, the demand is very low. Okay. For example, if you take the Indian steel industry, they make less than 0.5% of their steel is value-added products. I'm not talking defense, but value-added products. Rest are so-called commodity off-the-shelf products. Okay. Now, India is the world's second largest manufacturer of steel. Okay. But our value-added products is only 0.5% of their production value. Now, a country like Russia probably produces 1/2 of what India produces. Okay. So, but more than 50% of their steel is value-added. Okay. So that's what value addition can do to you. But we have low demand. The other problem is there is no assured demand, because if you make the material, you need to have these are all related to industry being able to invest. So these will fall in the regime of economical factors. Okay. Because unless there's an order, why will somebody set up the infrastructure that is required? And third is most of these are typically boom or bust or feast or famine situations. You have either orders much more than what you can handle at a given point of time, and then there's nothing. Okay. This is drought or flood kind of situations. Okay. These are very, very characteristic of advanced materials, especially for the strategic sector. The other one, which is very kind of unique to India, is that we normally don't have pilot scale infrastructure in most cases. For some cases, we don't have production infrastructure, but we know we need the infrastructure, but not putting the infrastructure is related to the previous 3 points. Suppose you need an infrastructure that is 2,000 crores investment, and your market value for the next 10 years is not more than 200 to 50 crores. How are you going to invest that? Who can you ask to invest that? And the last point is again linked to the same thing, because it's a feast or famine situation. And to make special products, you need to train people, need to train the workforce. Now, how are you going to do that? You need to create the skill set first, which we can do based on our lab experience. Like I told, part of scaling up is teaching them how to do it and working with them. You learn from them how they do it, so that you learn what are the controls that they have. The controls you have in the lab will not be the same controls that they have. Okay. But if they don't produce for a period of time, they're going to forget how they produced it. And materials, I think all of you know, materials and making materials and processing materials is very much like cooking, right? Even if you have done it for 20 years, tomorrow your shopkeeper changes the raw material on you, suddenly your sambar tastes different, or your dal doesn't actually cook. Right? Same number of whistles you have left in the pressure cooker, same amount of water you have ordered, but suddenly the dal is not cooked. So how do you take care of these problems? So these are all the, if I may use the word, the devils that lurk in the valley of death and pull you down. So this is a few slides on ICME. I mean, everybody today should be aware, but I just thought, just in case people are not aware, I'll show a few slides on this. So the next 10 minutes, and I'll close in about 10 minutes, would be just an assortment of things, just to see what we can do based on those problems that we have seen so far. So this is again from the same book, which I started the talk with in 2004. And this is originally due to Robert Shafrick, who worked at GE Aviation, and which eventually became the cornerstone of this book. And based on this, then the ICME recommendations came later. Of course, we'll see all that. So, but basically look at this. It takes 20 plus years if you want to have a new material class with no prior application experience, and a lot of that time goes in establishing the supply chain. If you look at the difference between case 3 and case 4, is this establishment of supply chain, and we talked about the infrastructure related issues and problems in the previous slide. Okay. So that was the book. Then it got developed further, and in 2008, again, the National Academies released the book on integrated computational materials engineering, which became the main driving force. And then there was an assessment after 5 years, which talked about implementation of that in the aerospace, automotive, and maritime industries. Just keep a note of that. I'll come back to that last one in a couple of slides from now. Okay. And then the materials genome, similar to a human genome and other things, was introduced in 2011. Okay. And basic idea was it gave the so-called materials innovation infrastructure. Mind you, we talked about digital data even then. That was 2011. Okay. Computational tools and experimental tools. And you can see all the fundamental things that it can have a great influence on. Okay. And again, this is extracted from that. Please note, in 2011, they said from the current 10 to 20 years, read the last 2 lines, they want to shorten the development time to 2 to 3 years. This is what was told in 2011. And that's part of that book. So now, why do they think that ICME can help you do this? These are again from the same book. The conventional approach is a very linear approach from discovery to deployment. Okay. And the whole idea behind ICME is to kind of make it non-linear by making each step talk to each other. Okay. In which case, you need to have greater and continuous interactions between the different phases. This is what now the collaboration across sectors, across segments comes in. Right. Now, this goes back to the 2013 report that I talked about. You see the main drivers which could do for materials would be, of course, I've written high performance steels, but that is in general about materials, are automotive, pipeline. You saw that, right? It said automotive, maritime, and aerospace. And these are just, I've highlighted things which are steel related. Okay. But these are all the things that needed to be done. But more importantly, you see that even in the US, when they made a 2013 assessment, that the industrial adoption is not at all widespread. You see right in the top, whatever is highlighted there, that no program has utilized. And even today, there are very small, there have been significant developments in using it for smaller components. It has been used to great effect in several aero components. Okay, it has made larger strides in automotive sectors. But when it comes to large scale defense structures, still, especially, it's not so prevalent in the industry. And why that's a problem is because you look at the bottom, because it requires a non-trivial initial investment in new technology. People will have to change their skill sets, and not only skill sets, mindsets need to change as well, which is sometimes more difficult. Okay. And because the starting capital costs are very high to change to this mechanism. So if you look at what you can do as a generic framework, again, this is very specific to materials, and we are very familiar with the individual boxes that are up there. You can look at chemistry, which is composition, thermodynamics, diffusion, manufacturing process simulation. So now start looking at this. It is integrated computational materials engineering, right? So already materials and manufacturing are almost getting together. You cannot think of them separately. Okay. It's almost working backward from the product, which is what I showed in that slide, in an earlier slide. You need to have quantitative processing structure and quantitative structure property correlations, which you can feed into quantitative models, and then you can do a product performance analysis to realize whether it will work or not. And with respect to high performance steels, within the country, this was my assessment maybe 4 or 5 years ago. We have changed somewhat. Many of the reds have turned yellow, okay, or turning towards yellow. But you see that we don't have many tools. we don't have much competence or experience in doing this. Of course, there are very specific small examples where they have done the entire chain. Okay. So this again for a steel making process, I just want to show how you might apply to steel. This for a steel making process and making different products. Okay. And the whole idea is basically like the focus on the bottom here, that you should be able to do processing structure and structure property and correlate that to property performance. If you're able to do these individual linkages, then you integrate those together and then get what you want. So a generic approach is that you see how to evolve an ICME like approach, and within DMRL we have done this for one class of materials already. Okay. But more importantly, you need integration and implementation, you see, from one length scale to another, from one computational to another experimental scale, from computational to experimental, and from discipline to discipline, and also organization to organization, and now sector to sector. I don't know how many of you have thought about it, but that's another talk of mine which was exclusively on ICME. But we deal normally, see, you deal from atoms to even structures that are as big as us. I mean, even if you don't go to astronomical distances, okay, you are dealing with 7 to 8 orders of magnitude normally, and you're dealing with 12 orders in time, because an atom jump or a vacancy jump, if you consider the time for that versus the lifetime of a component, not saying several thousand years, but maybe 10 years, 20 years, you're dealing with 12 orders in time and 7 orders of magnitude in length scales. This is what we have to work on. Okay. Again, I need not spend time on this. This is just to show that in steel making, for example, each one, how to divide it into sub processes is what this is showing, and you have to track the process. And I mean, there's a systematic way of doing it to look at how much is your capability in terms of implementing any of this. But again, going back to that, essentially what you will need to implement it, you will need to have very reliable experimental data. You need to have good design models and design data. And like we have already seen, you need to have some models which link structure property and processing structure. Models could be physical, empirical, heuristic, analytical, numerical. And you need these at these different scales. I just now talked to you about these scales. And then you need an integration environment which kind of puts all this together. A holy grail is you simply say, can I realize a digital twin? Rather than making a steel plate in the industry, can I then, okay, I've done it in the lab. Now I just feed it onto the computer. I know all the models. I know whether I can do it in the industry. Okay. But we are far, far away from that time frame. But that kind of gives you a direction. So lessons learned and still learning in terms of this. I should thank my colleague Dr. Shankara for putting this bunch of 3-4 slides. That multi-scale modeling is of course one of the steps towards acceleration of materials design. We need to take into account all these variations in chemistry, process parameters, and microstructural metrics. And many, many times we don't even know how to describe the microstructure properly. For example, look at the floor of this stage. What to describe the structure adequately? And that means how will you distinguish this stage from another stage? What are the elements that you need to specify? So that means human beings do a lot of things subconsciously very effectively, right? A small newborn baby recognizes its mother and father from other people. Right? Today, Google can recognize you, Google Photos can recognize you and say you are sitting in that photograph. But look at how much time it has taken. Human kids have been around for how many millennia? Right? So then the rest of it is that need to invest on high throughput experiments, and the word that you've been emphasizing again and again, because you need to do all of this collaboration. You practically cannot do it without collaboration. So this again just shows in terms of the implementation of ICME a couple of examples, where the first one, and this was a group that worked on computational aided materials design for a very long time. So you can look at the bottom left and right, and they took 10 years to do that in spite of involving some computational work. But if they went to a more integrated approach, they reduced it to 6. And the final the difference is not there on the right part of it. Incidentally, what is given on the right side, the value of death is essentially from TRL1 to TRL7, right? So if you're not able to do, and this is on the TRL, but that is for a component, but for materials, you look at it on the right side. So you'll have to do all of that. You see, even within the lab and at a pilot scale, you will have to do it repeatably, and essentially you have to show repeatability and reliability and get all the properties that you need to give the designer. Okay. So they were able to finish in 1 design iteration instead of 5 design iterations. So instead of 10 years, it took 6 years. Okay. This I already highlighted. If you don't have the pilot scale, which is where typically the TRL 3 to 4 to 7 is taken up. This is a problem we face in our country today. And therefore, we are actually doing experiments at full scale. And therefore, we are not able to generate enough materials to generate the data with the enough variability between batch to batch or one vendor to another vendor. We still are struggling to do that. Okay. So this is a problem that is kind of unique to us. Now the last 3-4 slides would be on the different roles of all of us. Now that we have set the stage, we have looked at what we can do. Okay. So again, starting from the user, what does he want? You have to meet the user requirements. And what these 3 agencies have to do, somehow you have to get together. Okay. Not tear yourself apart. That funnel is intended because I don't want anybody to run out of that. Okay. All of us have to be together, and you want material of required quality on time and within budget, and you want short lead time to maturity. I again talked about this in product, not just in knowledge, in product. And repeatability and reliability and consistency, we have spoken about this so many times today. And the more critical the component, the higher the level of performance and reliability that's required. And you, of course, many times they want drop-in solutions, right? They don't want to replace the entire setup. What is there, you should be able to change. Okay. Many times that is the case. So what we like to do, and I would request that all future questions can be directed to Dr. Seema, because she is our person in residence. I take the liberty of saying that. So it's a means to establish a strong research base. We want to establish also critical threshold mass of researchers and research expertise. Okay. So some of the points, again, these are my reflections, and we could debate on this, that we need concerted efforts. So the DIA-CoE is a step in that direction. We want a presence, want a continuous presence. We want faculty to work on a problem after problem after problem. We want faculties to interact together to solve system-related problems, not just one problem which he is interested in his own small domain. And to begin with, the Indian academia needs probably more hand-holding, and therefore, now this is the translation job between the labs and the academia that the DIA-CoE is supposed to do, taking input from both sides, is to convert the lab's requirement into specific problems which faculty can handle and which can be tracked with a figure of merit and can be tracked with milestones. And vice versa. So this is I put with industry. Okay, this is not with R&D labs. This is with industry. Okay. So until we create a culture where these interactions happen more naturally, now the interactions between academia and industry or R&D labs and industry, okay, we have to make conscious efforts to bring them together, because otherwise they think, what is there in it for me? They are not going to come to you. So this was again a timeline kind of effect where it simply shows that the initial, see 1985 to 1989, then it was 97 and 2000. So Ferrium 53 was shown in the earlier slide. So it's taken something like 15 years for a company that has worked on computational related work. And this is put here only to show that to begin with, the gestation periods are very long, and patience and sustained effort is very crucial. Okay. This we saw earlier, so I will not talk about it. So now what is the real challenge? Okay. This question is to this audience. Okay. Can you retain your interest over a 5 to 10 year time frame, knowing that there are problems not necessarily in your domain but in the other domain, and be willing to extend your hand to solve that problem? This is really the fundamental question. And to those of you who are students who will graduate and go out and get jobs in industry, you will have to now look at it from that side, look in and see what can be done. Because unless we do this, we cannot do high impact or groundbreaking or disruptive work. Industry, of course, should do its part, and it should offer, I mean, one of the things that we found, because this was, I did this work actually at that time for Ministry of Steel. We were trying to see what was going on. And we found that, you know, there are hardly any jobs at the higher level. Okay. So some of the ideas then is to develop mechanisms for R&D divisions to interact with academia and R&D, short to mid-term exchange of personnel, have realistic timelines, focus on the long term, but you have to ensure short-term progress is measurable and is in the right direction. And we need to ensure commitment all around. So for industry, again, I told about better jobs, they give fellowships, their internal R&D should be quite robust, and they should be able to attract youth and retain them for generating new ideas, and also they will be the repositories of skill retention for complex manufacturing. And therefore, a robust internal R&D of top quality can be effectively facilitated. Of course, this is to be done at R&D. Because today they don't talk, and again, this is strictly a personal view of what an academia, industry, and R&D organization like DRDO can do is in the short term, medium term, and long term. Again, this is not exhaustive or exclusive. These are just thoughts. They should do at least this much. Okay, is to generate new knowledge and provide support and help sustain competence for troubleshooting. And you have to produce a current quality and then evolve towards higher quality. And you'll have to augment the infrastructure. And the R&D organization really plays a key role because they are the ones who get to know the requirements and stay in touch with the requirements, map it onto the technology curve, interact accordingly with academia and industry, kind of act as the overarching bridge between the two. And together, the three, then we all meet the user or system designer's demands and requirements. Okay. So I think since I'm running short of time, I'll not go through this. I'll just probably skip through these slides as I speak. So sustainability is this challenge is very recent. I mean, we have been causing the problem for a very long time, but acknowledging the problem and thinking that we should do something about it is very recent. So now imagine it was difficult enough. Now you have to do all of this in an environment friendly, ecologically sound, sustainable manner. Now this adds a totally new dimension to that. And when I mentioned about extractive metallurgy and looking at chemical reactions and thermodynamics getting more prominence, it is simply because of this aspect. Now you have to add, therefore, science, engineering, technology to the economy. To that you have to add sustainability. Also, of course, ecology was there in the picture that was shown. Okay. So this again, I learned a lot because I was part of IIM. I think Professor Das talked about my role in IIM. So I was a core member of this, where we brought out a book on the circular economy of metals, the current status. And I happen to be one of the people involved in this. And we all know that there's a rapid loss of natural resources. Like I said, I'm just rushing through this because I don't want to delay this any further. But if you look at the last point, right? If you think the earth is 1 year old, in the last 0.2 seconds, we have got rid of 1/3 of earth's resources. That means like this, as compared to a year, we have got rid of 1/3 of the resources. So that's how serious the problem is. It's about extraction of different material classes. This is the amount of materials that we mined in 2021. And iron and steel is a very, very important component you can realize because you see, the total is 2.8 billion tons, of which 2.6 billion is iron ore. Everything else put together accounts for the remaining 200 billion. Okay. So now the real problem is this. Okay. If you look at even 2020 to 2030, the world's populations will become about the total thing will be 5.6 billion consumers, and we will need 2 planets to support us in terms of the resources that are available. In fact, today that number is at 1.6. Okay. That is because certain developed countries are consuming more than their resources, but because others are consuming less and it is available in the rest of the world, we are still managing. And if we aspire for a Western quality of living, then the world would need 5 planets. Okay. But today they say we have less than 1. Okay. And we expect that the amount of natural resources we extract will be more than double. So we need to move from a linear to a circular economy. Have a sip of water while I let you glance through this. Which means our consumption pattern, development pattern should all have to change. Right? You want to keep things more in use. Of course, this chart kind of thing in the bottom is that refuse means it has a maximum impact. Okay, on the average, circular evolution has a 50% impact. So if you reduce, then reuse, repair, refurbish, remanufacture, repurpose, recycle, recover. Okay. And again, there's a lot to talk about this in metals. It's a whole talk by itself, but I will not talk about it here. Basically, there are several opportunities for material science and engineering here. Okay. Because like I said, we are talking about natural resources and materials. So in closing, again, a concept to product involves 4 distinct cycles: lab scale development, pilot scale production, qualification and certification, and industrial production. And our goal is to shorten the time and cost without compromising the quality. And like I said, there are so many stakeholders and all of us will have to work together. Okay. And there needs to be continuous interaction between all of these people. And it therefore needs to be a cross-functional, multidisciplinary approach. And of course, like I've shown, ICMI, and now we have added, even though I did not talk much about it, the AI and ML, this can play a major role in traversing the valley of death, at least as far as addressing the technical problems are concerned. Of course, you could argue that you could even address economic and social problems, because you can do technically in such a way that you use more abundant material, you use material that consume less energy to produce, and so on and so forth. Okay. So this is basically, I'll go back and finish with the book that I started from. So these are already written in the book, and that is made in 2000, that was released in 2004. But each one of the statements is valid today as it was 20 years ago. Of course, this was already in the past. When they looked at what were the successful development stories, then they found that there was flexibility everywhere. There was a willingness to take risk. There was open communication without regard to hierarchy. Of course, they looked at academia, industries and all that. It was also focused on industries. And a sense of responsibility that replaces unquestioned authority. And the last point is more important, a commitment to success that goes beyond functional roles. You may still have a particular role, but do you have a commitment to the end outcome? So creating the culture that is willing to do all of that means that individuals must feel empowered to take risk. And like I said, this was more in an industry context. Therefore, the management must anticipate and plan for failure, and everyone must champion teamwork. Okay, and collaboration should be given precedence over individual accomplishments. So what this will mean is that engineers and scientists, again, this was with respect to industry, we can add academic researchers also here. It doesn't change anything. That you must be allowed to experiment, to think freely, and to fail on occasion. In fact, you look at it. Why it is written specifically, that is because today in academia, you really don't have a problem on failing. You do an experiment, it doesn't work, it doesn't work. Everybody agrees and moves on with it. But even in R&D labs and in industry, it's not so. So it has to be explicitly allowed. And therefore, to encourage innovation, it is in our government jargon, if you write for failure is not an option, you should read failure provides lessons learned in an innovative environment. And therefore, I mean, like they say, you have to fail fast and fail quick and fail early so that you learn and you take it and you go forward. Okay. So I think this is my very last slide. So ICME required integration on all of that. And I mentioned this earlier itself, but for traversing the valley of death, this is not enough. You also need an integration of minds and mindsets. This is perhaps the toughest challenge of all. Thank you very much.
Thank you. Thank you, Dr. R. Balamurali Krishnan, for your insightful and inspiring talk, which has undoubtedly enriched our understanding and fueled our curiosity. Now it's time for the Q&A session. For this, I would hand over the mic to Professor S.R. Meka, Member Secretary, Departmental Faculty Committee, to preside over the Q&A session.
Thank you. Thank you very much, Dr. Balamurali Krishnan. It is an excellent talk. So now it is open for discussion. So any comments or questions?
Yeah, what you said is that we should reuse, recycle and everything. We are doing the reverse right now, at least in India. Things lasted a lot longer earlier rather than today. I think practically every item that I use is lasting less.
Unfortunately, they are designed that way, right? They
Yeah.
don't want your phone to last beyond 3
Yes.
years. Correct. So that's why it's an overall shift. See, what we are, I'll let you complete.
No. Basically, we are effectively shifting to Western style.
That is true. See, the whole problem is because like in everything,
Yeah,
Our consumerism and consumption patterns are lagging the West by 20 odd years, right?
right.
So, and they are the ones who are pushing their market and products here.
Yeah.
So now, see, it's also linked to another thing where a particular generation's life cycle is also small. See, earlier, for example, when we talked about this, a grandmother used to hand over one big brass lamp whenever somebody gets married and say, my grandmother gave it to me, it has been in the family for 300 years, and today it is there. Today, try and find something that is modern which has been there for 10 years, right? Except as junk or debris. It is not in use.
No, that is, I
So-
mean, that is a real problem now, actually.
It is. That's why I say, I talked I gave another endowment lecture in IIT Kanpur about a month and a half back. And there I talked essentially only on materials and sustainability. So this part I've just extracted from that because I thought you can do advanced development, but if you do side of sustainability, you end up in bigger problems. So in fact, the biggest challenge right now is exactly what you said.
Yeah.
And that's why I close with that mindset part. Because now we are getting used to this lifestyle, right? So it would take a lot of effort to actually consciously engineer solutions which last longer. And the other thing is which stay longer in use. Okay. And even do you need it? This is at the consumer end, of course. You see, again, that talk focus thanks Ujjwal for bringing this up, because one point I did forget to tell is, as a country, because you also mentioned India, as a country, we still have to grow in terms of per capita consumption. We still have to grow because as a country, there are people who don't even have the basic good quality of living, decent quality of living. Forget about a very, lavish or extravagant quality of living. India's power consumption per capita is very low. India's energy consumption per capita is low. All your metal consumption is low. So for the country to grow, you have to somehow increase that. But can you do the per capita increase without creating greater damage? So that is why I said material science has a role to play in all of this, because unless you make materials which work better and which last longer. So basically you now have to think in terms of life cycle cost, and in the sustainability jargon, they talk of now no more cradle to grave. It is cradle to cradle. So you take less and less of Earth's resources going forward. And it's going to be a major challenge, but it's doable. A quick example is, for example, aluminium. To produce from primary raw materials like bauxite and other stuff, and versus if you recycle aluminum, the energy consumption reduces by 95%. To recycle aluminum, you need only 5% of the energy that it takes, even though aluminum is used less. For example, for steel, for every kg of steel that you make, it generates 2.2 kgs of CO2 emission. For every kg of aluminum, it generates 10. Okay. Of course, steel, you saw the quantity. So in terms of absolute numbers, steel does still a lot more. And right now in European Union, we are discussing yesterday also. So one of the major thrust areas is sustainability, clean economy versus green economy, hydrogen economy, and what you will do moving towards clean, green, and sustainable. In fact, for those who are interested, it's available on the internet. If you just type European Union 2030 manifesto, you will get it. It is all, in fact, they're putting more than 40 to 50% of their resources on converting each one of their manufacturing chains into more sustainable practices. But it would definitely be a challenge. But on the same count, it is a great, great opportunity for people working in the area of materials, because materials are the ones that can create the maximal impact.
Professor Abhishek.
Hello, sir. Thank you for the nice talk. I I would like to just, can you elaborate on the point that how can we increase or actually decrease the adaptation time of materials related technology? To just give an example, in semiconductor industry, for example, the adaptation of technology is much faster, right? They try to follow this Moore's law. What are the changes in materials
Moore's law
and
was
metals
not,
development?
I think she is better placed to answer this question. I'll maybe divert the question and I'll add to whatever she has to say. Why don't you pass on the mic to her? With her here, I should not attempt this answer, first of all. That is a problem. If she were not here, I would have told something.
No, you can still say.
Please go ahead.
Can I have the question again? Yeah.
What I was asking is that how can we actually reduce this adaptation period of materials and metals related technologies which are developed in labs, basically, but they take sometimes very longer.
And more importantly, why I diverted the question to you was, he says, see, semiconductor technology goes with Moore's law.
No, yeah. So Moore's law example you gave, that is increasing the density of the devices in a certain, on a certain wafer or in a circuit. So there, your base material remains the same. It is the processing technology which is letting you do that.
Right.
But the base material, to get to that kind of a maturity, to use it with reliability, then the whole cycle of whatever is mentioned for materials here. Of course, I would say that in terms of semiconductor materials, it is the substrate, the size is, so you are just increasing it gradually, but it does not have the scale as Dr. Bala mentioned about, the materials that you would require for making, for manufacturing something as large as a ship or a plane. So there, the scalability issues are entirely different from what you have in the semiconductor industry.
No, I understand your question. Just to elaborate further, let's talk about single alloy. Let's talk about steel, right? Because you said, say, semiconductor has like only one material class. We are only making advancements in terms of processing, right?
Yeah,
So
there are
can we make such
advancements
so
in
that-
terms of material also. There, but the scalability is not that you have in metallurgy. That is what I'm saying.
Okay, okay.
Yeah. I hope.
Yeah, it was. In fact, to add to that, see, for example, I think you look at, there are so many modern semiconductors, gallium arsenide, 3, 5, 2, 6, all that. But, right, but even today, right, silicon probably rules much of the consumer electronics at least, right? I mean, so, and so that means, like she rightly said, the base is laid. See, if you have the infrastructure once, in fact, that part I did not talk about. So one of the answers would be, if civilian adoption of materials is higher, okay, then this is where I talked about the difference in value added steel between India and Russia. See, India makes 120 million tons. Russia makes only half of it, 66 million tons or something. But 33 million tons that Russia makes, or for almost 40 million tons that Russia makes, is value added steel. Okay. So that means, that's what the economy comes in the point of it. It's not essentially a technical issue, right? So is the investor able to recover his money? That's what it will come to, right? Whereas when we say we make 120 million, and my value added is only less than 0.5%, then what? I'm not even making practically 1 million tons of special steel, right? 1.5 million maximum. I mean, it's not there. So now you see, where is 1, where is 40? That's what, no, if it's an answer I can give from your pocket, I'll give you, right?
Yeah.
See, I spent 45 minutes to tell you it is not a simple problem, isn't it?
Materials that we are going into for. So you have the material development and also the process development. Silicon definitely is the most mature technology, but to conceive of the application of a new semiconductor material and take it to usable integrated circuits or something for different applications like RF, the minimum cycle is now that the processing technology is advanced, you need at least a decade to get a new material into usable form. So I really do not know.
No, it is still the same thing, right? I mean, even there it takes 10 years. Yeah.
It's minimum 10 years, minimum. I mean, from the day it was thought that it can be used, that is what it is. That is what the cycle is like.
Thank you, ma'am. So, Professor Vivek, I think the last remark, there are a lot of exciting, discussions.
See, I think we need some professional agents between academia and industry. So who can sell a problem to academics that you solve this problem, and then he can sell the solution to the industry that this is the best solution. Then I think it will work, because we know agents can do wonders when we are stuck.
It is true, but that's why I said it. It doesn't, unfortunately, like I showed, RNA and industry should come together, right? So first of all, you should try to speak a common language. When if you let us, since I use the word language, if you insist on saying I am speaking French, he speaks Chinese, Find an interpreter for me. That means the French guy is not at all interested in learning the Chinese. It's not going to work because the interpreter is a third guy. He does not know your domain, right? Only you, and in fact, I think I'm very happy you brought this, and it's a very good point for people discussing after the talk is over. Maybe catch hold of him also and discuss. Is that, see, why is it that we want somebody else to facilitate? Yesterday, I'll take the excuse, I'll hide behind Professor Daniel and said, I've already brought this point yesterday to him. Why we always want somebody else to facilitate? Because all we have to do is be a little more open and say, oh, what's your problem? That's all you need to ask. Because exactly what you said, sir, is what is happening. And that is, in fact, the biggest barrier. You say, I am an academic, my job ends here. See, there was a slide which said, you take responsibility for success beyond your functional role. And today, we are interested in entrenching our functional role more and more, and especially when competition comes, we lose the spirit of collaboration and complementing each other because we want as an individual to prove nobody else knows this more than I do. It's true, right? I mean, yesterday I was giving, in fact, that is an analogy to what I'm about to say. Yesterday I was talking about this making bundi and laddu, you know. If each one is a great bundi of different color, different character, but to hold it together, you need a glue. Otherwise, you have fantastic bundis, but you will never have a laddu. Right? Now, imagine if all this is together, you mix it together, you make laddus and you can transport laddus. You cannot transport 40 different types of bundis around. Whereas you can put all of them, make one single laddu and everybody can have the laddu. Whereas you say, I am red. I don't care. I am red, I am sugar. If you want jaggery, it's your problem. This is been a biggest pain, and it's not an individual problem. It is just because industry, what do they want? They want a drop-in solution, right? Because you see, he's producing, like I said, steel plant, Rourkela steel plant, because I've worked very extensively with them, they cannot stop production. He's making 8,000 tons in a day. He's not going to be able to sit and say, oh, Dr. Bala, tell me what's going on. So I have to sit, like I said, I sat in the shop floor, I solved their, I said, okay, this is the furnace you have, what are the things you can control, you tell me. That's how we came up. In my lab, I changed one knob. There we came up with fuel to oxygen ratios for 20 burners over a 5-hour heating cycle. How it should be controlled. Because he said, देखिए साहब यही है मेरे पास क्या करना बताइए हम करेंगे. Suppose I said, this is my recipe here, 5-10 degrees plus minus 5 degrees, you heat treat for 5 hours, you will get the property. He says, this is the furnace I have, I shove the plate inside, take the plate out after 5 hours. So I had to sit in there and do it for the moment I sat and did it for the first plate. Afterwards, when they have a problem, he will send me all the 20 burner readouts and say, sir, this is what it is as a function of time. Now what adjustment can I do? Because for him, the calorific value of the, see, I am not a combustion, a refractory guy or anything. I studied about calorific value of fuel just to optimize that furnace. Otherwise, my fuels and refractories, if some of the older professors may remember, it was taught to us in BTech, one course, maybe one afternoon or one lecture. So I had to go and look up because he is using blast furnace plus coke oven gas as a fuel for the furnace. Each day its calorific value changes over a period of time. So then we have to tell, okay, this is the time. So what checks that he can use on the ground? And this is a uniquely, as far as I know, I should not say uniquely. I've seen probably India, America, a couple of other countries. This is a uniquely Indian problem. We have a great reluctance as academics to step into industry. We think that's a different world. And it is. But we have to understand their problems, and likewise I wrote that also. No, I said they also have to understand your problems. And yesterday we were discussing the same problem. Because why industry is not, because otherwise people go there, they find jobs are regular mundane jobs. They are not exciting jobs. Why they don't have exciting jobs? Where do the exciting jobs lie? The exciting jobs lie in this interface, right? What you can prove in the lab as promising, can I realize it in industry? Now industry will have challenging jobs. And today, because, in fact, they have told me, the question you asked, I've heard, and there, one of the top management people told me, they say, sir, वो क्या है सर, वो lab से आएगा सर, ये करो वो करो बोल के एक दिन पे जाएगा सर, हम ही करना है. And when the production goes on, he is the one who gets the scolding, no, not me. And sometimes his promotion gets affected. Like professors are evaluated on how many papers you publish. The shift in charge gets assessed on how many tons was there in a shift. And when I go, his tonnage goes down. In 3 hours, he produces 1/3. So I take permission from the very top. They say, nahi, your defense has strategic importance, karo. And then we try to do it when there is a maintenance between, because maintenance they anyway take 4-hour break. So take sir और उसके साथ और 3 घंटा ले लीजिए. So that means my reheating which starts previous night, I have to schedule with their maintenance. I can also say, here is my recipe. If you do it, it will come. If you don't do it, what I can do? And not only, because that problem was there also. That is why I said in that last but one slide, unless people go beyond their functional roles and boundaries, I think we will never make anything big. You will become big. There is no doubt about it. You don't have to have doubts about it. But whether you will contribute to something becoming big, that's a different story.
Thank you. Thank you. I think to add to that, I think we have DIA-CoEs and Madam is with us as an interface between, us and the academia and industry. So I think we can benefit from such initiatives. So one last, the remark or a comment.
I was really very much tempted to say certain things from my lifetime experiences, as well as still am experiencing due to my certain capacities, as well as still I am consultant of some industries. Due to some of my capacity, I move throughout India, still now, every month. And I move to many R&D and academic institutes and universities. I really find in India, we do really murder of talents. Truly, absolutely. In my last 40 years of R&D experiences, teaching experiences, and all these things, I heard that word, industry, academia, so many things, relationship, this, that, so many. But ultimately happened practically zero. Practically zero. In my last lecture, before my retirement, when I was delivering a lecture in management department, there I told that probably from where I started, I am finishing at that same point itself. It is a tragic part of my whole life. I could do nothing. Truly that. I have really a very good experience to see that DIA-CoE. I was not knowing about this earlier, at least in Roorkee. And I
think it is
asked
very
Sarmaji,
very
I asked Sarmaji, and then he told me that yes, it is last 1 month it started.
Yes.
In my lifetime, I was never a true academician only. I worked with industry, huge amount. Huge amount in India and abroad, both in Germany, which have found a tremendous drawback of our exposure of our academicians and students to our real need of market of industry. And still it is there, and we are at the same position. It is not like this, we don't have talent. We have huge talent of academicians, teachers, and most importantly, students.
Absolutely.
I have great respect for our students, But in most of the places where, when I move to many universities and R&D institutes, I tell them, you are really misusing your total talent and you are spoiling your time, because our system is like that, that you are not aware or you are not allowed to be aware of real need of market.
True, very true.
Whatever they are doing and they are thinking they're great. When I say them, and I say that what you are doing, you know, this is this. And where we are now, it is this. Why you are doing this thing? So we are not knowing about that. We have no system to lead our teachers and our students to know that what really required in the market in every sector of materials, mechanical, and everything. And that is the first and foremost job, I think. Please, madam, I would like to request you, because of my lot of experience in that area, try to find out a system, establish a system where you can make aware our, which Vivek has told is very correct, where you can make aware our teachers and students primarily to know that this is your target, this is your goal, this we need. 10 years, now I will say, is a very big time. In 1 decade, practically everything changes totally, is obsolete. So that 10 years word, it was valid maybe 50 years back. Now it is not more than 5 years.
That is
In
for
many
use side, from the use side.
Yes.
That is the challenge, because
That
our
is the
development
challenge.
cycles are still bigger.
And how to do it? Please, madam, in your office, I am very happy to know that you have some office like this. If you need, I can interact later on. For that, you should establish a system where our teachers and students can be really aware of the market need.
I agree with you 100%, sir. No problem. In fact, yesterday again, we were discussing the same thing. See, you can ask him.
I am finding change only in last 10, 15 years that it is changing.
Some
Really,
attempts are being made.
sometime.
And,
Yes.
And yesterday we are saying competence and capabilities, we don't have a dearth of talent, whether it is in this, and especially the students. And this demographic dividend, we should reap.
You know, I can tell you one of my most interesting interaction with Dr. Kakotkar sir.
Okay.
Great personality. Great personality. He told me many things, and when I discussed with, that is the time when after our bomb blast and everything, that we were suspended for many things. And we were really cornered that we have to do things ourselves. And he could do many things, and that is why we are here. In no other area, and aerospace also, except these two, in other areas, still it is not understood properly. Still it is. Please do something. How we can get interaction with industry to know the market need.
Thank you, sir. So I think industry academia has got barriers. I think we all know that that is what is bringing us to these enormous discussions. So there must be barriers. I think we should accept it and find a ways to cross over that barrier.
Yeah, in fact, like you said, the whole problem of talking about it for that long, nothing is happening. Is so that's why something has to move, and it has to reach a certain critical threshold mass. After that, it will sustain itself. Today, we are trying to establish that system, and that's why this conscious about, like in 15 academic institutions, we have set this up, and trying to, the DRDO has set up this industry academia centers, like in IIT Indore. There are 14 others, and 15 more, I think. Jodhpur also got inaugurated just last year.
So, thank you. Thank you. So we are now.
I would just like to say that, sir, whatever you brought out is definitely true. There has been less interaction. May I take
Please,
this?
please.
Time to, okay, so right now after this, I think we have an interactive session. Yeah, but I would just like to say one thing, that there have been mechanisms of the academia interacting with the defense labs earlier also through extramural research funds or through contract acquisition of research services. But there have been such mechanisms, but DIA-CoEs are clearly for translational research. So that means you have to translate your research in something that is usable. And as you said, it is recent. All I would say is that it is just a matter of getting to know what is required. And I appreciate that point that you made. And there are ways to know how at least defense requires what and how academia can get into it. That is what.
And just to add one more, sir, like you, there are so many people who have worked with industry, sir. It is not that they have not done. But unfortunately, that number is still a small minority.
Okay, thank you. Thank you for nice discussion. So I'm privileged to offer vote of thanks at the end of this very, insightful lecture. So we are truly honored to have you, Dr. Balamurali Krishnan, for, sparing your time and coming here. So, and delivering such a wonderful lecture. I think it is the need of the hour to focus on translational research. So give him a big round of applause to Dr. Balamurali Krishnan. So I take this opportunity to thank Dr. Seema Vinayak for taking her time as a director of the DIA-CoE at our IIT Roorkee. Ma'am, you highlighted the importance of collaboration, and we hope actually with this DIA-CoE we'll find more avenues. As the director of DMRL is here, and then we are, as a metallurgy fraternity, we look forward to take up some of the collaborative efforts in any of the translational activities. Thank you, madam. So we are thankful to Professor A.K. Sharma, our Dean of Faculty Affairs, for taking his valuable time and spending for the entire event. Thank you very much, sir. So, and highlighting actually the purpose and importance of having this kind of endowment lectures to actually trigger the interactions and, curiosity and, opportunities, exploration possibilities. Thank you very much, sir. So I'm thankful to Dr. Saurav Das for, my colleague who is also the office bearer of IIM, for briefing us about the activities of IIM Roorkee chapter and also the kind of opportunities which are available through this, IIM for the students and the faculty. Thank you very much. So I take this opportunity to thank our institute, especially our proud alumni whose generous support has actually made the way for having this kind of sustained lecture series of the Professor ML Kapur lecture series. And it makes so relevance in today's world for sustainability and all that, the contributions of Professor ML Kapur. So I thank Professor ML Kapur also possibly joining through virtually. So, and I also thank all the department, colleagues, students, staff, and the, the students, faculty colleagues, and the former colleagues here, who created the foundation for this department on which we are proudly standing today. And I thank each and every one of you in this hall and all those who are actually, viewing this through virtually. Thank you very much. So now I invite all of you to join for a one group photo, followed by a national anthem to, yeah. So I request all of you to raise for the national anthem now.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता